Well, hello everybody. Good to see you all. My first time in Verona, so that's exciting. Welcome to our talk. The name is Evolutionary UI, Change as a First-Class Citizen in the Modern Front-End World, which is a long title, but we'll get there. So first of all, hello. I'm Rufus.
And I'm Giamir.
We're both senior devs at ThoughtWorks, which is sort of like a bespoke consultancy all over the world. They have an office in Milano. We sort of focus on TDD, agile, pairing, that kind of stuff. We, like 1.5 years ago, we started the ThoughtWorks front-end community, which is an internal community of practice that focuses on advocating for best practices in the front-end space. So we provide resources, talks, presentations. We collect information from different projects that we've done with different clients. So that if a tech lead is trying to decide what framework to use, there's a wealth of information that they can refer to make that decision. So the reason we're doing this talk today is because a couple of our colleagues wrote this book called Building Evolutionary Architectures a while ago. It was a big moment for us at ThoughtWorks in general because one of the authors is our CTO, Rebecca. One of them is sort of our chief presentation giver and thought leader. That's Neil Ford. And then another one is now an ex-ThoughtWorker who is now the CTO at N26. So that's Pat. And we read this book, which has a lot of interesting advice about how to build architectures that scale well, that evolve gracefully without sort of losing the most important characteristics over time. But there was no mention made of UI. And I think that's sadly a little bit par for the course for sort of traditional architecture. UI is sort of usually an afterthought or not mentioned at all. So we thought we would take this opportunity to use the resources of the front-end community to put together a presentation on how to apply these principles of evolutionary architecture to UI.
So, and today is gonna go like that. First, Rufus will actually give you an overview of what we mean by evolutionary architecture. And then, like, we will present you a set of challenges that you will be likely to face when you want to build a UI that support constant change. We will then explore a couple of concrete examples of UI architecture built with evolvability in mind. And then finally, we will wrap up our journey with sharing with you a couple of things that may be or maybe not go wrong when you are actually building an evolutionary architecture. So let's dive in.
Cool. So before we can really try to apply evolutionary architecture to UI, we first need to understand what evolutionary architecture is. So I'm going to give you the 10-minute summary of the book. So we'll talk a little bit about what is meant by evolutionary architecture and sort of what are the key cornerstones of an evolutionary architecture. So I'll take a really short diversion to refresh you on your high school biology. So evolution in biology is the cumulative change of characteristics in a population over time. And I think the most interesting lesson in biology is that you cannot stop evolution. It's inevitable. It happens based on the current forces that exist in an environment. So it's inevitable. This should sound familiar to us as software engineers. Change is always going to happen, or you get left behind by the industry. We also know that business requirements are constantly in flux. This is our daily life. So if change is inevitable, why not control and guide it so that the change moves in a direction that works for us, so that it works in a predictable and safe way? So let's apply this to Pokemon. So this is an Eevee, and Pokemon can evolve into other kinds of Pokemon. So this Eevee can evolve into this badass fire creature, but it can also evolve into this badass water creature, or into this badass lightning creature. So this is fine and good, sort of in a free environment, but we as Pokemon trainers may care what evolutionary path our Eevee takes. So if we are particularly interested in this Pirion, then we may want to take some steps to ensure that this is the way that our EV evolves. So this is exactly the point of evolutionary architecture. So evolutionary architecture is supporting incremental guided change built in as a first-class citizen in your application. So to come back to this example, let's see what we might do here. So in order to ensure that only Vaporeons survive, we might want to create an environment which is amenable to Vaporeons. This is what a fitness function is for. So a fitness function is an architectural construct. It's meant to create an objective measure of the stuff that you care about. So it gives you an assessment of, for example, if you care about testing, I could give you an assessment of how well you're testing your application. And because you can run the fitness function over time at different points in time, you can see what the trend is and how well the architecture is growing or diminishing in that characteristic. So it turns out that even way before software, humans have been doing this for ages. We have understood the power of the fitness function for a really long time, for millennia, in fact. So man's best friend is the result of literally millennia of selective breeding. So breeders would select for a certain characteristic that they care about, like friendliness or the ability to hunt. And this is what results in the dogs that we know today, which are all the same species, by the way. It's wild. So we've been applying this stuff for a really long time. Coming back to our Pokemon example, if we had a bunch of EVs in a room and let's say, I know that's not really how it is, but let's say they just evolved randomly, and we wanted to select only our water creatures, then what we could do is we could introduce some sort of moat or some sort of obstacle that's only surmountable by a thing that can swim. So if we were to collect our Pokemon on the right side of the screen, the moat ensures that only those Pokemon can cross. So in this particular example, the moat itself would be a fitness function because it would determine the fitness of the Pokemon. So let's apply this to software. That was kind of a silly example. Let's take the next step and see how this relates to our daily work. So let's say you care about accessibility, which you probably do if you build a user-facing product. A fitness function for accessibility might be a measure that tells you objectively how well you conform to a certain well-known standard, such as the Web Content Accessibility Guidelines. They have like a couple of levels. So if your goal is to conform to like AA, for example, or AAA, then you could run Google's Lighthouse against your application at different points in time and not allow the build to pass if you have violated a certain part of the spec. Performance is another important one, since users bounce after 3 seconds on mobile if a thing doesn't load quickly enough. So a great way to keep your performance in check is to set up a performance budget fitness function. There's a lot of nice, like there's an NPM module out there, there's lots of stuff you can use. And this would just run as part of your build, and it would set like a maximum amount of bytes that your built application is allowed to be. Excuse me. Code quality is one that at ThoughtWorks is really important to us. There's many ways that you could try to objectively measure quality. It's really hard. It is a subjective thing, but one of the more common ones is cyclomatic complexity. So there you could just set an amount of complexity that your application is allowed to have, add it to a linter, and cause your test or build to fail when you pass that amount. Finally, testing, the classic example, set up a test code coverage gate, set a minimum threshold of percentage covered, so that you have to have enough tests to pass that threshold. So those are just some examples. Those are fairly straightforward ones that should hopefully be relatable to the work that we do every day. We'll talk about some more complicated, nuanced ones in a bit. But one other thought that I want to leave you with is that these fitness functions don't have to be automated. Of course, as developers, we want things to be automated. That's not always possible. Fitness functions can still give you a lot of value, even if they are not automated. Just to take Lighthouse as an example, yes, you can code it and put it into your pipeline, but you don't have to. You could also just put like a recurring event on your calendar and like run it manually every week or whatever. So we'll see some examples of both automatable and manual fitness functions in a bit.
Cool. So we're now moving on the second section of our presentation, where we actually want to show you a couple of challenges that you will be likely to face when you have to build a UI to support constant change. But before that, I just want to say that maintaining fitness function doesn't come for free. Like, it comes with a cost, as everything in software development. So the first things that you may want to do is actually like to understand if you need to account for your specific system for evolvability. And I'm going to help myself here with this graph that I kindly borrow from Martin Fowler's website. For the one who Martin Fowler that doesn't know who Martin Fowler is actually a chief scientist at ThoughtWorks, the consultancy that we're working for. And in here, like, you can see that we have in our horizontal axis time, and in the vertical one, a cumulative feature that we are adding to our system over time. So we essentially have two approaches here to go for building our application. We can, of course, go ahead and start building the application without really having an architectural vision. This may give you like a boost at the beginning, but of course, in the long run, it will actually slow you down, because you will start accumulating the so-called tech debts in your code base that they, of course, like will slow down your feature development. Another way that you can go on, of course, is to taking more time at the beginning to build a solid bedrock for your system. Of course, here, like, you are a little bit slower at the beginning compared with the first approach, but you're gonna reach a point where your investment that you made at the beginning are gonna be paid off. So what the question here is, what product are we building? Is that a prototype or a throwaway application? If that's so, it's fine like to skimp on design up front. It's fine like to, don't have to think about evolvabilities and fitness function and all of that. But if that's not the case and you want to build a system that scale, like, then it's worth investing in fitness function. So let's now like go through some of the challenges that we actually believe are quite hard on the UI space to build a system that is evolvable. So the first one, I think that you are all quite familiar with the JavaScript ecosystem, and it's definitely a fast-paced one. Like, every day in the JavaScript world, something comes out, and it seems like that we are sometimes even like reinventing the wheel. But like, I'm really excited like to be to take part of this community, because it's basically like one that we are always trying to address problems with different solutions. And although like although I like to be part of this community, these changes can be overwhelming for some enterprises. So I was one a while ago. I was one of these people that believed that AngularJS actually set a standard on the way we were building single-page application. Then we all know that React folks came around, and they actually say, okay, a component-based architecture is a better model to describe our UI. And we know that AngularJS went through a complete rewrite, and that it was basically like the second version that came out was completely incompatible with the first one. And this like for the joy of all these enterprises that actually invest a lot on standardizing their front-end code bases like to AngularJS. So what I'm saying is that JavaScript is like this happy puppy, running fast, discovering new tools, new best practices every day. I love that puppy, but of course, like keeping up with the pace, it's definitely a challenge. Another challenge that we have in the front-end space is about keeping UX consistent. So at some point, perhaps your system will become too big for being developed by a single team. So multiple teams will start to work on your system, and that's when you will start to see inconsistent user experience across your application. So this is because perhaps core primitives or your UI, like a core, like a button, will start to behave in different way in module developed by different teams. So what I'm trying to say here is that keeping UX consistent becomes a challenge when we do development at scale.
Here's a question. How many of you test your JavaScript? That's cool. I feel like that's about a third of the room, half of the room. I feel like if I'd asked this question a couple of years ago, the response would have been pretty different. It would have been a lot lower. And I think that's because the JavaScript itself is changing a lot. People are starting to realize that this is now a serious language. It's here to stay. We heard this morning how much it's been changing in the last 25 years. And so people are, I think, slowly dropping their preconceived notions about the language. Because so much complexity is shifting into the client-side applications now, there's a real need to test JavaScript. I recommend you do. But this also comes with some challenges. I think there's certain aspects of modern UI applications that make it pretty hard to test them with the current traditional approaches that we have to testing. So something that we've observed a lot at ThoughtWorks, not only on our own projects, but throughout the network of the ThoughtWorks front-end community, is that we're encountering a lot of tests that are quite coupled to implementation. And on some level, I think that this is because the surface area of the component can be quite large. By surface area, I mean its API, I mean the props that you pass in from the outside. I think particularly because it's now best practice to try to separate your state mutation logic from your view. Actually, I say it's now best practice. It's been best practice since the MVC days. But because it is best practice to separate state from view, a lot of the time, your actual view rendering components, require basically all data to be passed to them from the outside, so they can potentially have quite a large prop surface area. So this creates tests that need to know about the prop surface area and have to change as the props change. Need to rename a prop, change the tests. Similarly, because components exist in a hierarchy, they have a parent and often they have children. This requires a different mocking strategy. So usually, in like a really traditional unit testing approach, you would want to mock out the parent by passing in certain prefabricated test data, and you want to do something with the children. You might want to see that the correct props get passed down, whatever different approaches you might take to see that maybe that a child does something. So you require just a lot more setup. You require 2 levels of mocking of some sort, and you just need to know a lot about the data that the component requires. Usually with testing, we want the test to be flexible, robust, and meaningful. Flexible meaning that the implementation can change, and the test shouldn't have to be refactored as long as the business functionality stays the same. Robust means that tests should fail consistently or succeed consistently, that you can actually trust your tests. And meaningful means that your test should tell you stuff that's actually useful for you to know. If a prop name changed and I'm asserting on a certain kind of prop being passed down to a child, that might not be useful for me to know. The business doesn't really care about that. So there's a lot of challenges involved in testing well, especially testing at scale. Yeah, let's move on.
So partitioning complexity is actually a challenge for all the areas of software development. Probably most of you in here are familiar with terms like microservices, breaking up the monolith, self-contained systems. These are all ways to partition complexity, and they become pretty relevant when we want to build systems that are able to scale. An interesting trend that we observe in our industry as well is that we are moving into edge computing to accommodate more engaging user experiences. So the point that I'm trying to make is that a lot of the complexity that perhaps a few years ago lived in the backend system in the server side is now on the front end. And And also the front end comes with its own set of specific challenges that are really unique. Like, for example, working in an environment with unpredictable resources. How much CPU resources will I get from the devices that my user will actually use? How much network bandwidth will my user have? Or even as a developer, can I be sure that I can, develop a product with offline capability? So another thing is that the web browser, for example, have one single DOM and one main thread. And when we build system at scale, we are basically have multiple teams working on different front ends. And when we compose all these front ends, these resources, these browser resources are shared, which means that it takes only one bad module shipped by a team in order to make an entire application unusable. So all these challenges about partitioning UI complexity, they kind of become a hot topic, which is getting more and more traction in our community today.
Everybody's talking about it. Great. So now we know what evolutionary architecture is. We understand some of the challenges that exist, particularly in the UI space, or I would say maybe uniquely in the UI space. So we're now ready to go ahead and start exploring how we can utilize, how we can wield evolutionary architecture concerns, such as fitness functions, in order to drive ourselves towards architectures that are more evolvable. So we'll pick two examples of the challenges that we just showed you and show you how you might utilize fitness functions in those cases. So I'll talk about testing flexibility, first of all. We talked about robust, meaningful, flexible. I'm going to focus specifically on flexibility here because that's where, in the component-based world, we've seen a lot of growing pains. So I'm going to give us a little scenario here. So I'm going to give us a scenario. If you find yourself in this scenario, then it might be a hint that you are struggling with this particular challenge. So let's say that you're spending a lot of time refactoring your tests. You make a seemingly innocuous change, and suddenly you have to make a lot of trickle-down changes. Particularly as your code base grows, you feel that you're slowly getting crushed under the weight of your test suite. So having noticed this, you feel that maybe you need to look at your overall testing strategy, and you sort of suspect that you might have to choose a new strategy. So let's now think about how we can utilize fitness functions to drive us towards writing better, less coupled tests. Step one is going to be just rallying around what our current approach is so that we can see how we can use fitness functions to get away from that approach. Most likely, if you're testing your UI today, you are using the test pyramid as sort of the guiding light of your approach. The test pyramid has been around for a while, is the conventional wisdom around how to set up your various types of tests. The test pyramid is pyramid-shaped because it describes to you how many of every type of test you should have. So at the bottom, the pyramid is wider, so you should have more of these types of tests. At the bottom, we have unit tests, which test a specific thing, the smallest possible thing that can be tested, like an atom. Then we have integration tests. You should have less of these than unit tests because they're more expensive to run and they're a bit more difficult to maintain. These test several units in concert. And then finally, we have end-to-end tests, which test your entire system front to back. So these are usually browser-based automation tests using maybe Selenium or Cypress or something. Another thing to note is just that the relative expense of maintaining, writing, and running these tests is supposed to be different as well in the test pyramid. So the wisdom is that unit tests are more expensive than integration tests, which are more expensive than end-to-end tests. So let's say that we're an e-commerce business, and our shopping cart thing, our shopping cart widget, is the most revenue-driving part of our UI. So we want to make sure that this is covered well by tests, because if it's broken, even for an hour, it costs us a lot of money. So if we were to use the test pyramid approach to testing this, you might test each of the components independently. So you might have tests for the add to cart button. You might have tests for every individual, well, for an item component. You might even have a test for the item list component and for the remove from cart button. So as you're doing this, you're starting to notice, you're observing that maybe this is what's causing this painful refactoring. The components have a lot of props. You have to change them as the props change. And you're also using, well, frankly, you're probably using Redux. If you're not using Redux, you're probably using something similar to it, NGRX, whatever the view one is called, probably. Even if you're not using Redux, you probably have a couple of state-focused components that manage the state for you. It's just a really useful pattern to have, and it's gotten really popular. So you're also getting dissatisfied with the type of feedback that your view component tests are giving you, because your application can still be broken, but have your tests pass, because the state logic is missing. So you're not really feeling super happy about these types of tests anymore. You're also noticing that it doesn't really seem to take that much more effort to create integration tests, like adding multiple components together in a test and testing those. It seems to run almost as fast as the unit tests. And we're talking about like milliseconds here. So you're wondering whether the test pyramid relative sizes are really still accurate for this particular case. OK, so now let's see what are some fitness functions that we could use to get ourselves away from this particular type of testing. So our goal, remember, is to loosely couple our tests to the implementation. So one potential fitness function that we could use is disallowing shallow rendering. There are a lot of test libraries out there that provide a shallow rendering option. Usually this is used at unit test level to make mocking easy. Usually it provides capability to sort of reach into the component, look at implementation things, manually update stuff. Is considered by many people not a good practice anymore. We encourage you to read the blog by Ken C. Dodds. There's lots of articles that he's written about this. That explains why this is not really something that you maybe want to do. Among other things, it's just not very realistic. Users don't interact with things by like manually calling an onChange function. Even if you're, so that's why he wrote this thing called React Testing Library, which actually by design doesn't provide this capability. But if you're the vast majority that's still using Enzyme or whatever other library you're using in your particular ecosystem, you can still make use of this. So you could create a fitness function such as this lint rule, which Giamir has kindly written for you, that's available on GitHub, which will complain if somebody is using shallow in your code base. Add it to your lint, let it fail when somebody accidentally adds it, remove it. Straightforward. Here's another slightly more controversial one, perhaps. What if you were to disallow mocking everywhere except at the network level? Well, it would solve a lot of the problems that you've been having, because you now, by definition, you can't know anything anymore about the way that the data is used internally. So you're just providing a network mock, and because the data is only coming in from the network level, you, by definition, have to basically stand up the entire, probably not necessarily the entire application, but essentially an entire unit of functionality. So, traditionally minded testers might squirm at this, and might think that this is really extreme. But to that, I would say that something only really seems extreme to you or crazy to you if what you care about is different to what I care about. So if our goal really is loosely coupling test implementation, this might be a realistic choice. It all depends on the trade-offs that we're making. So in this case, we could institute a manual audit that happens regularly where we just look to see whether non-network level mocks have accumulated and then remove them. We could use something like knock or maybe just fetch mock. Any of those options would work. So now that those fitness functions are in place, you realize that they're broken given your current setup. So now you have to change something in order to pass them. So one approach that you've been hearing about is subcutaneous testing. This is something that we've been, there's been a lot of buzz about it internally at ThoughtWorks for maybe 2 years now. It's something we've been trying out at different places. And essentially, it is a more integration style test that focuses more on like the business value level than necessarily the code unit level. So you think this might actually meet your fitness functions pretty well. So if we were to take a sub-Q testing approach, then we might just test at the shopping cart level, because that is a discrete piece of business functionality. It's a sort of a cohesive piece. And you could even describe it as an architectural quantum. So in evolutionary architecture, artificial quanta are pieces of cohesive functionality that are essentially independent and can deliver a piece of independent like business value and are independently deployable. So in this particular case, if this shopping cart manages everything that it needs in order to function, you could even deploy it to like a private NPM repository or something and have different teams just drop it on their pages. So you could, in one way, you could describe subcutaneous testing as taking a quantum level view of testing. Now, of course, every architectural approach has trade-offs. Subcutaneous testing is no different. It just depends on what your desires are. So since our goal is loosely coupled test, which is one of the benefits that subQ testing can give us, this might be a good choice for us. But if we really focus on TDD, which we usually are in our teams at ThoughtWorks, then this might be more of a painful choice, since subcutaneous testing makes it really difficult, almost by definition, to drive an implementation from the test if the test doesn't know anything about the implementation. The good thing to note here is that even if subcutaneous testing becomes painful, we could throw it out tomorrow and never look back, as long as whatever we replace it with still passes those fitness functions. So that way you can sort of see how having those functions in place allows your system to evolve in whatever way it needs to, while keeping constant the characteristics that you really care about.
So let's now speak about the challenge of partitioning complexity in our UIs. So I'm just gonna go ahead here, and you can see an example of a newspaper website. It's nothing special. It has a search bar on top, like a content section on the left, another one on the right, and a related article section at the bottom. So if in your organization, you're actually splitting team in a way that are organized around a product, sometimes you can say that your team are cross-functional in the sense that are composed by people with different expertise, you will be likely to have a team that is responsible for the search capability, one for the content one for the ads, one for the related articles, and maybe you also using microservices, right, for the business layer and the data layer. But then everything needs to come together. So what do? You do this. How many of you are actually working with a similar architecture with a front-end monolith on top of several microservices? There are some few, maybe some. So the idea here is that you have an aggregation layer on top of these microservices, like an API gateway or a GraphQL service, a backend for front-end. And the responsibility of this aggregation layer is to aggregate information from all these different microservices to feed the front-end monolith. Now, the thing is that we may want our team to be completely independent. We want our team to own the product from the DBA layer to the UI. So how we can actually help to achieve that? We can perhaps start by setting up a fitness function that help achieve the goal of independent deployments for our UI. So in here, this is the idea basically of having different parts of your UI to be released to prod independently. So, and the fitness function could be shipping a product change to production. For shipping that, only one application needs to be redeployed. So in going back to the example that I just gave you earlier, let's say that I work for the ads team and I want to change something about my UI. In order to do so, if I also have to redeploy the content section or the search bar section for some reason, this will actually break my fitness function. So it will not ensure that my architectural characteristic is preserved. Another thing you may want to actually have in your system is scalable development. Scalable development is this idea of adding more devs, contributing to the same system, and get a proportional benefit on the amount of feature that we are able to deliver on the same system. So in here, a fitness function could be one that monitor the time that is spent for code changes to get to production. This time is also called cycle time sometime. So for example, you could put an hard limit of 30 minutes, let's say, from my changes to actually when I push to master to get ready to be in production. And I can also automatize, for example, this fitness function in a pipeline, and then forget about it. And then, you know, like maybe more team will join and will contribute to the system. And at some point, this fitness function will start to break and will become red and will actually like capture your attention and say, okay, something is happening in my system. I need to take action if I want my system to keep being like scalable. So a potential solution to address this problem is micro-frontends. So how many of you in the audience have heard this word before? Oh, okay, like, yeah, a lot of people actually. How many actually are using them? Oh, one person. I'm using them too, yeah. Cool. So I didn't want to come up with my own definition of micro-frontends. There are a couple of definitions out there in the wild. So I actually borrowed one definition from a colleague of ours, an Australian colleague of ours, Cam Jackson. So micro-frontends are an architectural style where independently deliverable front-end applications are composed into a greater whole. So by looking at the definition, it seems that they are a great fit to actually ensure that our architectural characteristics that we care about are preserved. And you can see here that you can just throw away the front-end monolith, and introducing micro-frontends kind of give the team the ability of owning the product end-to-end, from a DBA layer to the UI layer. So you have less cross-team coordination happening when you have to ship a change. And in here, you can actually see that no architecture is good in itself, and micro-frontends are no exception. We pick micro-frontends because we care about independent deployments and scalable development that are listed in the pros section here. But if my priority was to enforce UX consistency, probably I would have had to think twice before picking micro-frontend. Why? Because as we've seen, micro-frontends promote team autonomy, and they are also give you the potential for building a heterogeneous system. What I mean by heterogeneous system, I mean you could have team A starting actually building their front ends with React, and team B with Angular, and some other team with Vue, right? And of course, with all this diversity in your UI, it's getting harder to enforce UX consistency. You can still do it, but of course, it comes with the price of building, for example, a component library.
Cool. So the last thing that we want to talk about here is what are some of the gotchas if you try to use evolutionary architecture, and specifically fitness functions. It's a good picture, right? So what happens if fitness functions collide? This happens. This is actually a super regular thing. Let me give you some examples. Let's say you actually have chosen a performance budget. Well, we mentioned those earlier. What if you've chosen you've with code enforced that your application can't be bigger than a certain size? But then you also want to have a heterogeneous system, like Giamir just mentioned. So you want your teams to be able to choose different versions of React. Because if they had to use the same version of React so you can only ship it once, then that would actually tie them. That would make them less autonomous. So let's say, or even if you wanted to be able to use different libraries, if you want to have one team using Vue and one Angular and one React, for whatever reason you want that, if it is a goal that it's possible to do that, then that's of course in direct conflict with the performance budget, because this is going to just drive the byte size of your bundle all the way up. So what do you do here? Do you just throw in the towel and say that evolutionary architecture sucks? Well, to that I would say that the point of fitness functions is that they express things that you want. And sometimes things that you want are in conflict. So it is very possible to have two completely conflicting desires. In that case, what you have to do is make up your mind which one you want more. So fitness functions, when they collide, are meant to spark a conversation about priorities. So this is sort of the meat and potatoes of architecture, is trade-offs. So at some point, you're then going to have a conversation around which one is more important.
So, and if there is one thing that I learned by working as an agile consultant, is that you cannot really predict an architecture in advance, because in our job, business requirements are changing constantly. So the best that we can do, we can actually like bet on something. So we can pick a couple of architectural characteristics that we believe that they will help us like on the long run for building the specific product that we're building. And but because they are bets, right? It can happen that you pick a bad fitness function, or even more likely, you can pick a fitness function that was good up until a certain point, and then it start to become obsolete or even like dangerous sometimes. Let's take, for example, like a code coverage threshold that you have like as a fitness function. And you know, when you started a greenfield project, you started to have this threshold because you want to make sure that team members are actually testing the UI. Because you pick like this fitness function, you will soon see that after a while, team member and people will start to add in tests just for the sake of make the code coverage tool happy, right? And this kind of collide, for example, with testing in a flexible way. If you are interested, like on what Rufus was talking about before, like this collides with that because you would have tests, more and more tests that are tied in the to the implementation detail, and actually evolving that UI, it will become harder. So what do we do when we pick this bad fitness function? We just revisit it. So you may want like start to think again, or what was the goal that this fitness function was helping with. Perhaps you don't need that fitness function anymore. Perhaps you can focus on thread rather than having a hard limit, right? But like in short, don't be afraid of change your fitness function. They need to evolve as your UI architecture evolves.
So that's really it. We've made all the points that we meant to make. So we are just going to leave you with this TLDR so that you know what you should walk away from this presentation with. So first of all, remember that an evolutionary architecture is one that supports incremental guided change. Why is this important? Well, it's important because change is inevitable. Your system is going to have to change for business reasons, for technical reasons. It's going to have to happen. Just think of the example that we heard in the keynote this morning in the war between ASM.js and native client, where ASM eventually won just because it was apparently built in a more evolvable way and ultimately was able to turn into WASM.
Yeah. We've also seen that making a UI evolvable is challenging. Things like the fast-paced JavaScript ecosystem, like keeping UX consistent when we do development at scale, partitioning complexity in an environment with unpredictable resources, testing in a flexible way. Like, these are just some of the challenges you will be likely to face when you want to build a UI to support constant change.
Yep. And last but not least, if you also want to wield the power of evolutionary architecture, then start by defining what's important in your system. This is probably the most important architectural conversation that you're going to have. Once you have that, try to build objective fitness functions that give you a clear measure of to what extent you're succeeding in meeting your goals. Make sure to apply them regularly. Put something on the calendar, however often you need, every week, every month, to revisit them, to make sure that they run and give you useful feedback in time for you to change the implementation so that you don't actually pay too much of a cost when things go wrong. Finally, review your fitness functions regularly. Keep an architectural decision record. Write down what they are, why you chose them. Make sure to revisit them regularly and make sure that they're still serving your needs so that your application is evolving in the way that you want with the characteristics protected that you want to keep. Thank you.
Thank you.